All right, so the plan for today is just to continue with chapter 8, hypothesis testing. Um, so last time we talked about z-test for mu. We're going to kind of go back through that, do another example in that, move on to t-test for mu, and maybe get to z-test for proportion today. So that's kind of the goal for today. And then I also have listed here our next several class meetings. So we have 5 more class meetings after this one, and then kind of an optional review session during this time on 5/8. So on the Wednesday the 8th from 10:30 to 12:30. Note that the final exam is going to be very similar to the to the midterm exam. There will be a sample exam posted. The final will be taken on MyStatLab using Examity. And because of that, the time frame is flexible. So you can take the exam anytime between Friday the 3rd and Friday the 10th. Be very careful to note this end date is Friday, not the typical Sunday end date. That's just because of when the end of the semester falls and so on. So the end date, Friday the 10th. But again, you can take it anytime during that 1 week period. It'll be open a little earlier than Monday. That way you have the weekend before if you want to use that weekend. The formula sheets and distribution tables are posted on Blackboard. And so that's the final exam week. Since we're not taking the final exam, like, quote, in class, it's a college requirement that I offer something during the standard kind of final exam time. Obviously, I don't want to really cover actual material because I don't want you to feel obligated to show up on for a class meeting halfway through final exam week, and especially when we would be most of the way through our final exam week of availability. So this will just be kind of an optional review session, basically like an office hours time, that if anybody wants to pop in, you can, or if I have multiple people, then we can do kind of a review session of whatever topics folks want to go over. But this is kind of the plan for the next few weeks. Also, the bootstrapping supplemental lecture is on YouTube. I posted it in the just our standard YouTube playlist. So it's the most recent video as of right now. And after I post today's lecture, it'll be the second video from the bottom. The section 7.4 homework, it was set to be due this Sunday, but since it's already Wednesday and I just got the lecture up, I pushed it back a week to the 28th. So the bootstrapping homework not due until the 28th. I would recommend getting it started a little earlier than that, though, because hypothesis testing, like I mentioned before, is somewhat challenging material, and you don't really want to be trying to do the hypothesis testing while doing the bootstrapping. So if you can knock that out, this week or early next week, that would be ideal. And of course, you have, I'm sure, projects and other exams and so on coming up. So don't let too much get pushed all the way back till the end of the semester. And then also to help you out with bootstrapping, I posted a couple of supplemental Excel files, so 2 of them on Blackboard. One is more along the lines of some demonstrations that I used that Excel file in the lecture just to kind of show how it works, how bootstrapping works, and where we might want to use it. And then the other one is kind of an Excel file that's set up pretty nicely for you to use on the MyStatLab problems. So you can find that in the supplemental material folder under chapter 7 and 8, and then under the confidence intervals subfolder. And I think it's the first 2 files there. It should be pretty clearly labeled which ones are for bootstrapping. Okay, just give me 1 second. I'll be right back. Okay, and then the last thing before we get back in hypothesis testing, the quote of the day for today, really kind of 2 quotes. I kind of think these, in a sense, go together or kind of complement one another, or depending on your perspective, maybe two different points of view on a similar topic. One is from the philosopher Friedrich Nietzsche, from his book Beyond Good and Evil. And it's a pretty famous quote in philosophy, this one, like gazing into the abyss. Whoever fights monsters should see to it that in the process he does not become a monster. If you gaze long enough into an abyss, the abyss will gaze back into you. There are more poetic translations. He obviously wrote in German, so there are more poetic translations maybe that are a little more fun to read, or you might hear a different way, but that's the basic idea. And I mean, I think this quote probably is something like an onion. There are just so many layers to it, or so many different interpretations or thoughts about what exactly he means here, or maybe he means to say a lot of things, and that's why it's just a couple of sentences. And then from the Silmarillion, which if you're familiar with Lord of the Rings at all, the Silmarillion is a book that's kind of the backstory, the kind of creation story of the world of Middle Earth that the Lord of the Rings takes place in. So a lot of people have read like The Hobbit or maybe Lord of the Rings, but the Silmarillion is a book that goes along with those. And a quote from the Silmarillion: "Those who defend authority against rebellion must not themselves rebel." So I think especially in light of the kind of monster quote up here, we can see the parallels, the similarities. And I think somebody who has studied Nietzsche and who knows about Lord of the Rings might also see some differences between the two, but some interesting contrast between them. Anyway, that's the quote of the day for today, or two quotes of the day for today. Okay, so moving into our chapter 8 material, as I mentioned last time, when we get into hypothesis testing, it's not so much the calculations, like the mathematics, the table lookups, that are the difficult part. It's really the difficulty really comes in when we have to decide what calculations to use where and how to interpret the results of those calculations. And we talked quite a bit about what hypothesis testing is and what the goal is last time. And we also worked through this example last time. I want to briefly review what we said last time, because I know that the logic is kind of complicated, kind of complex. And then I also want to work back through this example again. And I know that we worked through it last time, but I want to work through it again. Last time we went through this example where we were kind of like building the method as we went through it. I want to go back through it and do it a little more cleanly, and now that we hopefully understand where everything comes from. And if you understand hypothesis testing at this point, if you understand what we did last time, if you're like, yeah, I got it, great, you're ahead of the game. But I know that most folks on the first pass, it's just a whole lot being thrown at you. So that's why I want to basically go back over everything we did last time, obviously much more quickly, just so that we kind of see that again. And then we'll work through a fresh example 2 down here after that. But I think it does benefit us to go through this logic of hypothesis testing several times. We did the narrative, we talked in general about it, we went through an example, and I think going back through what we did last time is time well spent. Okay, so what is the idea of hypothesis testing? The idea is we have two hypotheses. We call them the null hypothesis and the alternative hypothesis, H0 and H1. And the null hypothesis is the hypothesis that gets kind of the benefit of the doubt. It's the default, the status quo, something like that. The alternative hypothesis is what we are, in some sense, attempting to show evidence in favor of. We're attempting to prove, in some sense, statistically, the alternative hypothesis. Typically, the alternative hypothesis is the one that we want to say, the one that we kind of want to be true. And we give the benefit of the doubt to the other side of the argument, and we try to present sufficient evidence, statistically significant evidence, we would say, to overturn the null in favor of the alternative. Remember, we set up the null and alternative hypotheses to be mutually exclusive and exhaustive so that there's no overlap between them and nothing is left out. So they're kind of perfectly complementary. but we typically write the null hypothesis as something like, say, mu equals number, not like mu greater than or equal to number. And again, the reason that we do that is the kind of equals that endpoint is the most conservative null to test against. If we can reject the null in favor of the alternative for that kind of equality, that endpoint, then we could reject in the null in favor of the alternative for any other null that we might be interested in. And we use the example of a jury trial where the null is not guilty or innocent, and the alternative hypothesis is guilty. We presume not guilty. We go through a trial, the facts, the evidence are presented, and only if there's quite a bit of evidence to overcome a very high bar, only if there's evidence beyond a reasonable doubt that the person has committed the crime, do we switch from a not guilty to a guilty decision. Failing to prove guilt is not proof of innocence. So if I fail to reject the null, that doesn't, say that we think the null is true. We might still feel like it's more likely than not that the person's guilty, but just not enough to overcome that very high bar. There are two ways we can make an error. We can make a type 1 or a type 2 error. The type 1 error is when we reject a null, even though it's true. Type 2 is when there's a null hypothesis that's false, but we fail to reject it. I don't know why these two fonts are slightly different. sorry if that bugs you. I just noticed that. So the type 1 error rate, we call that the significance level. It gets the notation alpha, and that's the number that we typically peg to something like 5%, sometimes 10 or 1%. Those are pretty common significance levels to use. The alpha, the significance level, is used in the calculations that we do for hypothesis testing to decide whether we reject or do not reject. The type 2 error rate, beta, we don't really directly use that in our calculations. There are some rules of thumb as to what beta might be for a given alpha, but for the purposes of this class, we don't really talk about beta all that often, the type 2 error rate. We do kind of understand that the reason we don't want to just push alpha as close as we can to 0 is that when we lower alpha, beta increases. So there is a trade-off between the two. So we're not just free to say, well, I mean, if I get to pick my type 1 error rate, why don't I make it like 1 in a billion or something? Well, because your type 2 error rate, we understand, would be very, very high in that case. So we kind of philosophically use beta in that sense, in the sense that when we decide what type 1 error rate, what significance level, what alpha to use, we kind of have in the back of our mind that we got to pick something kind of reasonable. And typically that means 5% or maybe 1 or 10%. Those are the typical significance levels that are used. Okay, so I mentioned that. Okay, so I think that is a pretty good recap of the general kind of background behind hypothesis testing. And then let's go back through our example that we did last time. This time we'll go through, it'll be a little cleaner, a little smoother, but it'll remind us of how all these calculations work. And then we'll move on to a fresh example, and we'll see that this example too will be a little bit different. It'll have an extra little nuance that we'll have to address. Okay, so we have, it's reported that the national average credit card debt is $32.62. Our college believes our students have less credit card debt than the national average. We take a sample, we get X bar observed of $29.95. And again, we don't just want to jump to the conclusion and say, oh, because X bar observed is less than $32.62, we can make the claim. We realize that X bar observed could be less than $32.62, possibly because of sampling error, or possibly because of an underlying truth that our true mean is lower than 32.62. We're trying to tell the difference between those two here. We're trying to ask, is $29.95 so far below 32.62 that it's very unlikely that it's due to sampling error. And in the sense of in the wording of the narrative, that we would need a minor miracle to get this just by sampling error. And if that's the case, then maybe it would be more reasonable to say that we think that the actual mean is below 3262, that this would provide statistically significant evidence in favor of mu being less than 3262. And again, we want to make this claim. We want to do our due diligence and make sure that we have statistical support for it. We have our sample size of 50. We're assuming that we know that sigma is 1100. And our question is, at the 5% level of significance, can the college make the claim? Okay, so first we set up our hypotheses. With any hypothesis test, that's a good place to start. We note that we're making a claim about the mean. We want to say that our students have less credit card debt than the national average. So if mu is our students' credit card debt, we would like to claim that mu is less than 3262. We'd like to make this claim and have support for it. The null will write as mu equals 3262, and this is kind of the most conservative of the mu's, bigger than 3262. If I can reject for a null of mu equal 3262, I could reject for any other null further to the right of that, any other mean further to the right. Now, before I start my calculations, I always start with the statement, assume that H naught is true. Remember, what we're saying is I got a sample that seems to be kind of discordant with my null hypothesis. If my null was true, how unlikely would it be to get such a sample just by sampling error? So we have to start with the assumption that H naught is true. That also gives us kind of a bit more meat to work with, so to speak. We can now peg the middle of that X bar distribution. Remember from our central limit theorem, X bar is normal and is 50, it's bigger than 30. Well, if I just said it's normal with mean mu, I don't know what mu is, but again, because I've assumed H naught is true, and H naught is that mu equals 3262, I now know what that number is. And sigma X bar equals sigma 1100 over root n over root 50. So if H naught is true, this is what my distribution of X bar looks like. Now I have a sample mean, X bar observed, of 2995. Remember, I'm trying to provide evidence that the mean is less than 3262. If I were to reject the null in favor of the alternative for an X bar observed of 2995, that would represent a certain amount of evidence. But an X bar observed of 2994 or 93 or 90 or whatever further to the left would represent stronger evidence, right? Stronger evidence against H naught and in favor of H1. So if I rejected 2995, I would also reject anywhere further to the left. We call this a left tail test. And it's a left tail test because our alternative hypothesis has a less than here, mu less than 3262. So the kind of strong evidence against the null in favor of the alternative is whenever X bar observed is way to the left, if it's in the left tail. If I rejected 2995, I'd also reject anywhere further to the left. This area here, we call this the p-value. p-value, or often we just write p, it's the probability of making a type 1 error if we reject for this sample. It's kind of the actual probability of type 1 error if we reject, or it's the probability that x bar, the random variable, is less than 2995, or it's the probability that z, from this point forward, this is just a normal distribution calculation. Its probability z is less than 2995 minus the mean 3262 over the standard error. And let me get my calculator on screen. So 1100 over root 50. Or about 156. Or this is the probability. Z is less than, let's see what this turns out to be. Negative 1.71. And this I can just look up on my normal table. Close some of these other things I have open here. Here we go. I can look up probability z less than negative 1.71 on my normal table. So here's my negative 1.7 row, negative 1.71, that's 0.0436. So this is my p-value. This is the probability of making a type 1 error if I reject for this sample, if I reject the null in favor of the alternative for this sample. My significance level is 5%. I can say since my p-value is 4.36%, and that's less than 5%, or alpha. Alpha, my significance level, is the maximum allowable type 1 error rate. Since the error rate that I would see if I rejected for this sample is less than the maximum allowable error rate, or since p is less than alpha, I reject H naught in favor of H1, and I would proceed forward under the presumption that that our students' mean credit card debt is truly less than the national average. I would feel comfortable making that statement in marketing materials or whatever. And if anybody questioned it, I could show them this sample along with this analysis to back it up. So one way of saying this is I reject H naught in favor of H1. Another way of saying it is something like the sample that we obtained represents statistically significant evidence in favor of H1. Or we simply could say, therefore, we can make the claim. Therefore, we can make the claim at the 5% level. So those would all be pretty similar ways of saying basically the same thing. Now, we took this approach up here. This was the p-value method. Oh. And sometimes this is a nice approach to take, particularly if I mentioned last time that in fields like finance and economics, a lot of times they want to kind of test at the 1, 5, and 10% levels. So a lot of times they would present their evidence as this sample is, significant at this level, but not at this other level. So if I want to test against several alphas, if I wanted to test against an alpha of 10%, I can see that 4.36% is less than 10%. I can reject at the 10% level as well. If I wanted to test against the 1% significance level, I can see that I cannot reject at the 1% level. So a finance or econ journal might say, we can reject at the 5 and 10% levels, but cannot reject at the 1% level. And typically they wouldn't say it in a narrative like that. Often these finance and econ papers have like big charts with tons of numbers on them, and often they'll just associate asterisks with each number. So one asterisk meaning just one star after the number meaning significant at the 10% level, two asterisks meaning at the 10 and 5% level, three asterisks meaning at the 10, 5, and 1% level. So when you look through this whole chart, you can see pretty quickly what are the more significant numbers and what are the less significant numbers. We talked about another method, the rejection region method. And then there's also a third method, the critical value method, that we didn't talk about last time. It's pretty similar to the rejection region method, so we'll kind of lump it in with this discussion. So if I wanted to test one sample against several different significance levels, the p-value method would be a great option. Because if when I change alpha, when I change my significance level, my 5% to say a 1 or a 10%, I didn't use that until the very last step here. So that doesn't change any of my calculations. My p-value stays the same. And then I just have to do one comparison less than or greater than for each new alpha. What if I was planning to repeat this process a bunch of times? Again, like maybe a quality control engineer who wants to do the same kind of test on 10 machines, every couple hours. Wouldn't it be nice if I just was able to write down on a slip of paper a number and compare 2995 to that number? What if I could say, okay, for this test setup, sample size 50, the standard deviation, 5% level, and so on, what's my cutoff X bar observed? Where I can say if I achieve an X bar observed to the left of this number, that's statistically significant evidence in favor of H1. That's then I have the ability to reject H0 in favor of H1. Or if I see an X bar observed to the right of this number that I've written down somewhere, then I fail to reject H0. Can I just find such a number? If I'm repeating the same process a whole bunch of times with different samples, that might be better for me. If I tried the p-value method for each new sample, I would have to recompute the p-value. I'd have to do all the work from basically from this beginning step here for each new sample. It will be much nicer if I could have a rejection region where I can just say, this is the cutoff X bar observed. To the left, we can reject. To the right, we cannot reject. Well, we start off the same way. Just like above, assume H0 is true. That lets us anchor our normal distribution at 3262. And X bar is normal with a mean of 3262 and standard deviation sigma X bar of 156. That's that. 1100 over root 50 turned out to be 156. What I would like to do is I would like to come up with say a lower bound L or a left bound L that represents a cutoff X bar observed, where I say I can reject H0 if X bar observed is less than L, and do not reject if X bar observed is bigger than or equal to L. I would like to make a decision criterion like this. Instead of comparing P to alpha, I want to compare X bar observed to this limit. I want to ask, is X bar observed in the rejection region or not in the rejection region? Well, I know my cutoff X bar observed is going to be the one with a type 1 error rate of 5%. So really, I'm looking for the 5th percentile of this normal distribution. So L is the 5th percentile of the distribution of X bar. I know that I have a relation Z equals X bar minus mu X bar over sigma X bar, or that X bar equals mu X bar plus Z sigma X bar. Again, these calculations should look very similar from the confidence interval section, right? Point estimate plus Z times standard error. That was our confidence interval formula. Very similar ideas here. To get the 5th percentile of the distribution of X bar, I first find the 5th percentile of Z. I can find that down here pretty easily. I see area to the left of 0.05 is associated with a Z index of negative 1.645. So I have my mean 3262 plus a negative 1.645 times sigma X bar is about 156. So this will be 3262 minus 1.645 times 156. And that gives me about 3005. That's my cutoff X bar observed. So I can say I reject H naught if X bar observed is less than 3005. Do not reject if X bar observed is bigger than or equal to 3005. That's my decision criterion now. And now I can say since X bar observed is 2995, that was the number given in the problem statement. Since X bar observed is 2995, which is less than 3005, putting it in the rejection region, in this region over here to the left. We reject H naught in favor of H1. Or we can make a similar claim or similar statements as above. Since X bar observed is less than 3005, our sample represents statistically significant evidence in favor of the alternative hypothesis. Since X bar observed is less than 3005, we can make the claim that our students' credit card debt is less than the national average, and so on. We can make all of these same similar statements. So we get kind of the same end answer, reject H naught in favor of H1, either way, but we get there through two different paths. One path, we compute a p-value, the actual probability of a type 1 error if we reject for this sample, and we compare that to the maximum allowable type 1 error rate. That's super nice if we want to use the same sample and compare it to different significance levels. Or down here, we have a situation where we find the cutoff, X bar observed, the cutoff where we can generate a rejection versus not generate a rejection for that sample mean. And then we compare the actual observed sample mean to that cutoff of 3005 we found to determine whether we reject or don't reject. That's super nice if we have lots of similar samples with different sample means, and we want to quickly determine for the different samples, should I reject or not? Providing that these samples come from kind of the same setup, right? Same sample size, same underlying standard deviation, same significance level, and so on. Now we have a third method that's closely related to the rejection region method, and it's called the critical value method. So one thing I might realize up here is my X bar observed is like $29.95, right? It has a unit associated with it. But so did these guys. And this one, and therefore so does my my cutoff for the rejection region. So in the rejection region method, I'm kind of doing all of my work in some sense in like units of the original data. And again, that's a perfectly reasonable thing to do in some situations. But sometimes it can be better to compute a critical value. This is going to feel pretty similar to a rejection region. We're basically going to be doing the same thing as the rejection region method, but we're going to be using z-scores instead of x-bar distribution numbers. And so again, just to remind us, we have our null and our alternative. And then as always, I say if H naught is true, then I can do two things. I can first note that this is a left tail test. Again, because of this mu less than 3262, only in X bar observed that's far to the left would be strong evidence in favor of the alternative, and X bar observed far to the right would not be strong evidence in favor of the alternative. So this is a left tail test. And then I can do two things. I could compute a Z critical and a Z observed, and then ask, is Z observed to the left of Z critical? If Z observed is to the left of Z critical, reject H naught. Otherwise, if Z observed is bigger than or equal to Z critical, do not reject H naught. So my decision criterion looks, can't quite get them both on the same screen, but it looks very similar to the statement with X bar observed versus a number. But the difference here is we're using z-scores. So Z critical is the Z index with 5% area to the left. We have a 5% level of significance. And we have a left tail test. So this is the 5th percentile of Z. And again, we found that that was negative 1.645 from our Z table. What's Z observed? Move this down just a little bit. What's Z observed? Well, it is X bar observed minus what I'll call mu naught, the null hypothesized value of mu, over sigma X bar. It's really just the z-score for 2995. It's this negative 1.71. So it's 2995 minus 3262 over, I think this was 156, right? Yeah, 156. and that was negative 1.71. And now we can say, since Z observed of negative 1.71 is less than negative 1.645, which is Z critical, this less than is because it's a left tail test. We reject H naught in favor of H1. So this less than has to do with it being a left tail test. If this was a right tail test, this would be a greater than. This less than has to do with it being a left tail test. If this were a right tail test, the signs would flip. This less than is always this way. We're always looking for P less than alpha, whether it's a left tail or right tail test. Because P is the probability of making a type 1 error, I always want that to be low. But this number, 2995, or this number, negative 1.71, is related to X bar observed. And if it's a left tail test, my strong evidence is when X bar observed is far to the left, or when Z observed, therefore, is far to the left. Where if it was a right tail test, if everything was flipped, if I was trying to argue that I'm providing evidence that the mean is bigger than some hypothesized mean, I would want to show that X bar observed was quite large, quite far to the right. Okay, so we have our three approaches, the p-value method. Again, sometimes that's a nice version to use. The rejection region method, sometimes that's a nice way to go. In the critical value method. The nice thing about the the critical value method is when we look at maybe some other hypothesis tests, for figuring out a p-value or figuring out a rejection region wasn't really bad in this context because I had a normal distribution to work with, and that's a pretty nice distribution to work with. What if I had a distribution that was not so nice to work with? Maybe like a chi-squared, or maybe some other kind of distribution. Then it might be nicer to just kind of stick to these distribution indices. So when it's not so easy to find a rejection region or a p-value directly, something like that, that's when the critical value method really shines. So we might see that a little bit when we talk about the t-test for the mean, but we'll see it even more when we talk about some things at the end of the course, like ANOVA or goodness of fit or independence tests, things like that. So that's where this critical value method really shines in those kind of examples. As far as the types of problems that we'll be doing in, say, z-test for mu, it's probably a toss-up between the three methods. For t-test for mu, finding a p-value to any good degree of accuracy is kind of difficult. So rejection region or critical value might be the way to go. Although we will see that we can reverse engineer the t-table a bit to get an estimate on a p-value that is probably going to be accurate enough for what we need. And then also z-test for p, any of the methods will work. So for all practical purposes, any of these three methods will work for basically anything that we'll do in chapter 8. But again, when we move on past chapter 8 to some of the stuff at the end of the course, that's where we really see the critical value method being used a lot more. We essentially, after chapter 9 or so, really won't talk about rejection region or p-value pretty much at all. I mean, we'll talk about it when Excel computes it for us in some examples, but as far as, doing calculations or something, we're going to be looking at the critical value method from that point forward. Okay. So now let's move on to a fresh example. And we're going to see there's a nuance here that we have to handle. Okay, so in example 2, we have a scenario that I've kind of mentioned before. We have a quality control engineer working for a food company. They're assessing a juice dispensing machine. The machine is supposed to fill bottles with 16 fluid ounces of juice. And importantly, it's bad to overfill or underfill the bottles. Right? If we overfill the bottles, we're probably making a mess, or even if we're not making a mess, we're giving away free product. If we underfill the bottles, well, we're cheating our customers, right? We're giving them on average less than they should be getting. It's probably bad just because of ethics, but it's also bad because if our competitors or a regulator or somebody comes in and figures out that we're on average underfilling our bottles, that's either going to get us in trouble or make us not look good or whatever. So if we have reason to believe that the true mean fill volume for a certain production line is no longer 16 fluid ounces, we'll take the machine offline, we'll recalibrate it, right? We'll investigate it, recalibrate it. But of course, this is an expensive process. So we lose production capacity. We have to, have engineers recalibrate the machine and so on. That's going to be time consuming, expensive. Well, we don't want to do that for no reason. We want to have strong evidence that the mean fill volume is no longer 16 fluid ounces before we do that. So we have a sample that we took from this machine, and we want to know based on that sample, is there statistically significant evidence at the 5% level that the true mean fill volume is different from 16? And then we'll also look at what happens with the 1 and 10% levels as well. What is our sample from this machine? Well, we took a sample of size 10. We're assuming normality here, so we can use all of our nice central limit theorem results and everything that comes from that. We get X bar observed is 15.92, and we'll assume that we have a lot of experience with these machines, and we just kind of know the standard deviation is 0.1 fluid ounces. We want to determine whether this sample represents statistically significant evidence that the mean fill volume is no longer 16 fluid ounces, and that we should take the machine offline and recalibrate it. Again, looking at this, we might say, 15.92 isn't exactly 16. The naive approach might be, since X bar observed isn't exactly 16, shut down the machine and recalibrate it. But we know that there's going to be some sampling error. So the question is 15.92 so far away from 16 relative to all of the other parameters, the standard deviation, the sample size, and so on? Is it so far away from 16 that it would take a minor miracle for it to be due to sampling error? In which case I should presume that the mean fill volume is no longer 16, shut down and recalibrate? Or is it not all that far away from 16, with consideration of all the other parameters? Is it not so far away from 16? Do I think it could very reasonably just be due to sampling error and not strong evidence to shut down the machine? That's what I'm trying to figure out here. So what are my hypotheses? I'm making claims about mu, the true mean fill volume of the machine. And my question is, do I have evidence that the true mean fill volume is different than 16? In other words, mu not equal to 16. I kind of presume I give the benefit of the doubt to the mean still being 16. I mean, we built these machines, we calibrated them, we went to a lot of effort to make the mean fill volume 16 fluid ounces. So I'm not going to, my default is going to be that it's still 16 fluid ounces. I'm not going to just shut down the machine arbitrarily. But if I have a good bit of evidence, if I have statistically significant evidence that the mean is no longer 16 That's when I reject the null in favor of the alternative, conclude the mean is no longer 16, shut down and recalibrate. So what would be strong evidence against H naught and in favor of H1? Well, an X bar observed much larger than 16, or an X bar observed much smaller than 16 would be really strong evidence. Very large or very small observed mean fill volume would be strong evidence that the mean is no longer 16. So we call this a two-tail test. This is the nuance that we have to be careful about here. This is a two-tail test, where up here we had a left tail test. It was a one-tail test. In a one-tail test, there's only one direction for my point estimate, my X bar observed in this case, that gives strong evidence against H naught and in favor of H1. In a two-tail test, there are two directions, right? A big deviation in either direction would lead me to reject H naught in favor of H1. So let's go through our three methods: p-value, rejection region, critical value, for this problem. So let's start with the p-value method. And as I mentioned last time, if you were doing a homework problem, or certainly if you were doing an exam problem, you wouldn't do all three methods. You pick which method seems like it's going to work best for the problem, and you do that method, you answer the question, and you're done. We're just doing all three methods so that we don't have to have, so I can have two example narratives instead of 6, and we can get familiar with the example narrative and then see how it applies to each of the methods. So we don't need to do all three methods for every problem. We would typically pick one method and answer the problem and be done with it. So with my p-value method, I say, okay, assume H naught is true. That's always my first thing that I say before I start my calculations. I can apply the result of the central limit theorem because I assumed normality here. So even though n is 10, it's a small sample. It's coming from a normal distribution, so no problem with applying the conclusion of central limit theorem. Since I assumed H naught is true, mu x bar is 16. And sigma x bar is my known sigma, 0.1 over root 10 over root n. And let's figure out what that is. 0.1 over square root of 10. And that gives me about 0.032. My distribution is centered at 16. Again, why do I assume H naught is true? That seems like kind of a silly thing, doesn't it? Like, in a sense, we're trying to prove H naught is false and H1 is true, roughly speaking. We're trying to provide evidence in favor of H1 and against H naught. And we start by assuming that H naught is true. That kind of seems a little strange. Well, we assume that H naught is true because what we're asking is, I have a sample that seems to be discordant with H naught. Could that discordance just be explained by sampling error? Could it be just chance where H naught is actually true, and I happen to get a sample that's a bit farther to the left than I expect, but could very well just be due to sampling error? Or is this discordance so large? Is my sample so unlikely to get if H naught was true, again, that I would need a minor miracle to explain it, and that instead I reject H naught in favor of H1, because that seems like the more reasonable thing to do. So that's why we start with assuming H naught is true. It might seem like a silly thing to do at first glance, but that's where the logic is. 15.92 is to the left. This is my X bar observed. If I rejected the null in favor of the alternative for 15.92, I would also reject for 15.91 or 15.9 or 15, right? Those would all be X bar observes that represent stronger evidence against H9 in favor of H1. So if I rejected here, I would reject anywhere to the left. But something that I should note is there's also symmetry about this problem, right? This is a two-tail test. If I had run this sample and gotten a X bar that was far to the right of 16, I would have also rejected. So in other words, if I reject for 15.92, that's 0.08 to the left of 16, well, I would have also rejected if I had gotten an X bar observed that was 0.08 to the right of 16. So I also have this kind of mirror image rejection region, or this mirror image type 1 error contribution from 16.08 to the right as well. So this area over here is really, it's kind of my p-value, but it's only 1/2 of my p-value because I have this mirror image on the other side also contributing to the error rate. So in a two-tail test, I kind of basically just do the same calculation I did above with the one-tail test, and I just multiply the numbers by 2. So my p-value, often which we just call p, is, well, this left tail area is the probability that X bar is less than 15.92. That's this left tail area. And then I just have a mirror image of that on the right, so I just have to multiply this by 2. This two-tail test, we multiply the p-value by 2. That's recognizing the fact that in this particular case, we got an X bar observed that was a bit to the left. But in other cases, we could have gotten an X bar observed that was a bit to the right, and we might reject for some of those as well. If we reject for 15.92, we'd also reject for 15.9 or 15, but we'd also reject for 16.08 or 16.1 or 17 on the other side. Okay, well, at this point, this is just a normal distribution question, right? Getting this all set up and deciding what a p-value is and all of that is new. These are newer ideas, but answering the question right now, this is just normal distribution stuff. So this is probability z less than 15.92 minus the mean of 16 over the standard deviation 0.032. Or this is what? Negative 0.08 over 0.032. That's 2.5. So that's twice the probability z less than negative 2.5. Okay, so let's come over to our table. We'll look for the area to the left of negative 2.5. I see that's 0.0062. Or this is 0.62%. Doubled is going to give me 1.24%. So my p-value is 1.24%. I can say since my p-value 1.24% is less than, remember our significance level was given as 5% up here. Since our p-value is less than 5%, our alpha, our significance level, since our achieved type 1 error rate, if we reject for this sample, is less than our maximum allowable error rate, we reject H naught in favor of H1. We conclude the mean fill volume is no longer 16 fluid ounces, and we shut down the machine and recalibrate. That's costly, but it's necessary in this case. The statistics suggest that it's necessary. Now, the follow-up question was, what about the 10% and 1% levels? What if alpha was 1% or alpha was 10%? And we can see very clearly the p-value doesn't change. We didn't use alpha at all until the very end. So we reject at 10% because, again, 1.2%, 1.24% is less than 10%. Do not reject at the 1% level because 1.24% is not less than 1%. So the significance level alpha that is given in the problem statement that has to be decided on before the experiment is run, what this does is this controls that type 1 error. It gives the maximum allowable type 1 error rate. And remember, we can push it down. We can say require a type 1 error no more than 1% instead of 5%, but that comes at the cost of a higher type 2 error rate. We can relax it, use 10% instead of 5%, and that gets us the benefit of a lower type 2 error rate. We haven't really done any calculations with type 2 error rate, but we just know that kind of philosophically that is true. Practically speaking, for figuring out what the type 2 error rate is, we either use maybe a rule of thumb, or we have to make some assumptions that we kind of overlay on the problem and then can make some calculations for the type 2 error rate. Any questions so far? Okay, so let's go through example 2 again with the rejection region method and the critical value method. Apparently I was in a new window or something there. There we go. So the rejection region method. Remember, what's the idea here? Again, we always start with assume H naught is true. So we have our distribution. X bar, mean of 16. And the goal here is to create a cutoff. And I want to have a cutoff, X bar observed, fill volume, where maybe I can say that if X bar observed is to the left of this number, L, then I reject it all in favor of the alternative and conclude that the mean fill volume is no longer 16. But remember, this is a two-tail test. So I also want to have a symmetric part of my rejection region. I want to have an upper bound as well. I want my rejection criterion to be something like if X bar observed is to the left of L or to the right of U, then X bar observed is sufficiently far away from 16, my null hypothesized mean, that I don't think that it's just due to sampling error. I reject H naught in favor of H1. Or if X bar observed is between L and U, do not reject H naught. So here I have kind of two rejection regions, to the left of L or to the right of U. This looks a heck of a lot like a confidence interval, right? That's more or less what it is. There's a little nuance that the center of the interval is not X bar observed, but it's 16 instead. But if we centered around X bar observed and compared that interval to 16, versus if we center around 16 and compare that interval to X bar observed, that's essentially asking the same question. Remember when we were in the confidence interval section, we actually asked these kind of questions about confidence intervals, and we can now see that we weren't really off base at all in asking those questions. Okay, so how would I compute such a rejection region? Well, I would see that L and U are the center of the interval, which we previously had called the point estimate, but now is just 16 because, again, we're assuming we know what the mean is, plus or minus a z index. This is going to be the z index where half of the error rate, half of the maximum allowable error rate, is in each tail, times my standard error. What was my standard error? 0.032. Let me actually write these down here. So here I have 5% between two tails, or 2.5% per tail. So I'm looking for z 0.025. And I actually have that. Like for a 95% confidence interval, that gives me a z number of 1.96. Or I could look up 0.0250 in the middle of my table, and I see that I get negative 1.96. So this is 1.96. We have the plus or minus here taking care of the, whether we use the plus or the minus, it doesn't really matter. Right, this looks exactly like a confidence interval. The only difference is I'm centering this interval at 16 instead of at X bar observed. So 16 plus 1.96 times 0.032. That gives me 16.063. And my lower bound, the same thing, but just with a minus. 15.94. Or 15.937, we'll say. If X bar observed is less than 15.937, or if X bar observed is bigger than 16.063, then my sample mean is too far away from the null hypothesized mean. I reject H naught in favor of H1, conclude the true mean fill volume is no longer 16, shut down the machine and recalibrate. If X bar observed falls between these two numbers, then it's close enough to 16 that I think it could just reasonably be due to sampling error. And I don't have evidence that would suggest that I shut down the machine. It's not right on 16, the X bar observed, but I wouldn't expect it to be with sampling error. It's close enough that it could reasonably just be due to sampling error, not indicative of something underlying that's wrong. And now I can look at my X bar observed, 15.92, and I can say since X bar observed equals 15.92 is to the left of the lower bound, I reject H naught in favor of H1, conclude that the true mean fill volume is no longer 16, shut down the machine and recalibrate. We can do something very similar for the critical value method. Once we've done the rejection region method, we actually have all of the information we need for the critical value method. So here I can say for this two-tail test, Z critical is plus or minus 1.96. I have two critical regions, one to the left of negative 1.96 and one to the right of positive 1.96 for X bar observed that are far to the left or far to the right, respectively. Z observed is X bar observed minus the null hypothesized mean over sigma X bar, or that is 15.92 minus the null hypothesized mean of 16 over 0.032. And we have that up here as negative 2.5. We had done that calculation as part of the p-value method. And just to be clear what the decision criterion is, if Z observed is less than negative 1.96 or Z observed is bigger than positive 1.96, we reject H naught. Otherwise, if Z observed is between negative 1.96 and positive 1.96, do not reject H naught. And we can see clearly, since Z observed of negative 2.5 is indeed less than negative 1.96, we reject H naught in favor of H1. We conclude the mean fill volume is no longer 16 fluid ounces. We shut down the machine and recalibrate. Are there any questions so far? So like I mentioned, I don't think any of this math, these calculations, are really new to us, right? I mean, this just looks like a confidence interval. The rejection region above, if we kind of look at this just looks like a one-sided confidence interval. We did an example of that. But really, it comes down to why are we doing the calculations? What calculation should we do? And then what's the interpretation? Okay, so let's move to the next topic, the next type of test. Here we have a t-test for the mean. We could probably guess what's going to cause the t-test to come about, but let's go through the narrative and see if we can spot a difference between this one and the previous ones. So, for example, a city would like to advertise that the average commute time to work in their city is less than the national average. The national average commute time to work is reported to be 25.4 minutes. The city takes a sample of size 25 and computes X bar observed as 22.1 with a sample standard deviation of 5.3. We assume the commute times to work are normally distributed. At the 10% level, can the city make the claim? And we probably notice that we're given the sample standard deviation instead of the population standard deviation. Up above, we assumed we knew population standard deviation. So we did a z-test for mu. similar to how in confidence intervals, when we knew the population standard deviation, we had a z interval from u. And just like in confidence intervals, when we estimate the population standard deviation by the sample standard deviation, in addition to estimating the population mean by the sample mean, there's a little bit more variability, more volatility in the system. And we have to account for that. And the way we account for that is using the t distribution instead of the z. It has slightly heavier tails. That accounts for that extra variability. We do the same thing here with our t-test for mu. But aside from the fact that we're using a t distribution and the t-table, the philosophy is essentially the same. So we started by setting up our hypotheses. We're interested in making a claim about mu, our city's average commute time to work. We're trying to argue that our average is less than the national average. So the thing we are trying to provide evidence in favor of is the alternative that mu is less than 25.4. And the null, therefore, is mu equals 25.4, which really encapsulates all of the mu's bigger than or equal to 25.4. If I can reject against the null of 25.4, I can reject against any bigger null with no problem. Okay, let's take a critical value approach here, critical region approach. So we'll start by assuming H naught is true. And then we can calculate this thing, x bar observed minus mu naught over, but not sigma x bar, but s x bar, or x bar observed minus mu naught over s over root n. And again, we knew that when we had a sigma instead of an s, this was z distributed. This was distributed as standard normal. When we have an s, this is distributed as a t. So this is our t observed. And we'll compare that to a t critical. We note that this is a left. It's the left tail test. So our question is t observed less than t critical? If it is, we reject h naught in favor of h1. We can make the claim. If it's not, we don't reject. Okay, let's do our calculations. Well, t observed isn't bad. That's just plugging in numbers. X bar observed is 22.1 minus the null hypothesized value of mu is 25.4 divided by S is 5.3 over root n is root sample size 25. So if I come over to my calculator, I have 22.1 minus 25.4 for the numerator. That's divided by 5.3 and then times 5. That over root 25 on the bottom, that over 5 on the bottom flips up top and becomes a times 5 overall. So I have answer the numerator over 5.3, that's still in the denominator, and then times 5 because that flipped up to the top. So just be careful with your order of operations and so on. But this gives me negative 3.11. I'm feeling pretty good about this. This is a 3 sigma event. Seems like it should be significant. But let's do our due diligence. Let's just check and be careful. If we bring up our t table, so here I have a left tail test. So I'm searching for a one tail area. Oh. One tail area is the significance level, and here we're using a 10% level, so one tail area of 10%. And my degrees of freedom, just like in the confidence interval section, really the same underlying mathematics here as back there. My degrees of freedom is n-1, or 24. I want to find a t index with 24 degrees of freedom, one tail area of 10%. One tail area of 10% is the rightmost column. 24 degrees of freedom is this row. And it looks like 1.318. Now, keep in mind, this is a left tail test. I'm looking for areas in the left tail. I mean, really, this gives me areas. This really gives me areas to the right. So this is right tail areas of 10 or 20% or 5% or whatever. To flip that to a left tail area, I just use the symmetry. But I just have to remember to insert that minus sign where it's needed. So my t critical here is negative 1.318. If I made that mistake and didn't put in the negative, I would basically always get a rejection. Or I would think that I always got a rejection, and make a mistake. So negative 1.318 for t critical. My t observed is negative 3.11. And I can say since t observed of negative 3.11 is less than left tail test, so less than negative 1.318, which is t critical, we do reject H naught in favor of H1. And our city can make the claim. We can, put this in our marketing material or whatever. And if anybody were to challenge it, we could present them with this sample along with this analysis, and that's our supporting evidence. Now, again, somebody might balk at using the 10% level. They might say, oh, you should have used the 1% level. That's not something we can argue mathematically, right? That's something that has to be chosen at the beginning of the or before the experiment, before the sample is taken. Okay, let's also do a rejection region. So assume H naught is true. Then what do I know? I know that I have a one tail test, a left tail test. And I know that I have, I'll put kind of in quotes, X bar is distributed like a T distribution. It's really X bar once we standardize, once we subtract off the mean and divide by the standard deviation. And so I'm looking for this lower bound, or this left, this bound for the left tail. That's the cutoff where I have exactly 10% area in that left tail. This is where my p-value is right at 10%. And again, we can just think back to our confidence interval section, and we know that this is going to be the center of my kind of quote X bar distribution. If we assume H naught is true, that's going to be 25.4. And then we just do minus this thing we call T alpha. This is a one tail area of 10% with degrees of freedom of 24. times SX bar, or S over root 25. So what's this going to be? It's going to be 25.4 minus, and again, one tail area of 10%. Degrees of freedom 24, that's where that 1.318 came from. And then S over root 25 is 5.3 over 5. And we just compute this on our calculator. 25.4 minus 1.318 times 5.3 over 5. That looks right. And that gives me right on 24. And again, my decision criteria here would be if X bar observed is to the left of 24, because it's a left tail test, we reject H naught in favor of H1. If X bar observed is bigger than or equal to 24, do not reject H naught. Again, if you're ever confused at which direction things would point, just think of one extreme versus the other. If I got an X bar observed that was really, really low, like 1 minute, would that be good evidence to make my claim or not? Yeah, that would be really great evidence. If I got an X bar observed that was like 4 hours, that would be really terrible evidence to make my claim. So I know this has to be a left tail test. I know I'm looking for when my X bar observed is to the left. That's when I can reject the null and I can make the claim that I'm trying to make. And here I could say, since X bar observed of 22 point something, 22.1 is indeed less than 24, I reject H naught. H naught in favor of H1, and I can make my claim. I can claim that my city has a lower average commute time to work than the national average. Any questions on this so far? Okay, let's look at example 2 then. And we have what, about 12 minutes left. I think we should be able to get through this one. And then we'll leave z-test for proportion to next time to kind of wrap up the chapter 8 material. So example 2, a college believes that their students sleep on average at least 7 hours per night. The college, I don't know why there are so many spaces here. The college takes a sample of 10 students and finds a mean sleep time of 7.64 hours and a sample standard deviation sleep times of 1.08 hours. We assume sleep times are normally distributed. At the 1% level, can the college make the claim? So let's let mu be the true mean average sleep time for our students. Mean average sleep time sounds kind of strange, but I mean, take an individual student, take their average sleep time across a whole bunch of nights, and then that's a number for one student, and then you have a bunch of those, and what's the mean of those numbers? So it's the mean of the averages or something, I don't know. But so the null and alternative hypotheses are claims about mu, this kind of mean average sleep time, whatever you want to call it. And we're trying to make the claim that our students get at least 7 hours of sleep per night. So we're trying to provide evidence that mu is bigger than 7. And we're going to test that against the null that mu equals 7, which again encapsulates all of the mu's less than or equal to 7. If I can reject against a null that's right at that borderline, I could reject against any other null that's more that's further to the left of 7. Okay. Now we assume H naught is true. Again, we have a sample, 7.64 hours for our X bar observed. That's a bit bigger than 7. Is it just a little bit bigger than 7? It could easily have occurred by just sampling error, or is it so much bigger than 7 that I say, okay, this couldn't reasonably have occurred just by sampling error. I have to conclude that the mean is actually bigger than 7. Not that I have to, but the statistical evidence leads me to that conclusion. Okay, so if H naught is true, let's use the critical value method. So we have T observed is X bar observed minus the null hypothesized value of mu over SX bar, or S over root N. And we compare that to T critical. We note that this is a right tail test. We haven't seen an example of a right tail test before, but here we go. This works very similarly to a left tail test, just kind of things are flipped a little bit. The inequalities are flipped, some signs are flipped, but the idea is essentially the same. But it's a right tail test, it's a one tail test. So we're looking for a one tail area of 1% and degrees of freedom. While our sample was of size 10, degrees of freedom n minus 1 is 9. We can compute T observed pretty easily. It's X bar observed, 7.64, minus the null hypothesized value of mu, 7. If the null was true, this would be kind of the deviation of X bar observed and the actual mean. And how many standard deviations, how many standard errors away is that? So over S over root N, the sample standard deviation, 1.08, over root N, root 10. I see my numerator is just 0.64 divided by 1.08. And then that root 10 that's on the bottom in the denominator flips up top. So I get a times square root of 10. Or it gives me 1.87. As an aside, if you didn't follow all of those, the fraction details that I was saying, you could definitely do 0.64 over parentheses 1.08 over square root of 10. We have a closed parentheses to close the square root of 10, and then another closed parentheses to close the denominator. You get the same number. So you can do it that way as well. It's a little bit more typing in the calculator, but if you don't see why the square root of 10 flips up top, you can do it that way. You get the same answer, no problem. So my X bar observed would be 1.87 standard errors above the null hypothesized value of mu. Is that far enough that I would say that I don't think that's just due to sampling error? Let's see. So what's T critical? Again, I pull up my T table. I'm looking for a one tail area of 1% with degrees of freedom 9. One tail area of 1%, that's this column. Degrees of freedom 9 is this row. So I'm looking for 2.821. Remember, X bar observes that are far to the right, that are well above 7, give me better evidence, give me stronger evidence against H naught in favor of H1. So T observed being bigger than T critical, this is a right tail test, being further in that right tail, T observed being bigger than T critical. that's when I generate a rejection. I reject H naught in favor of the alternative that the mean is bigger than 7. Otherwise, do not reject H naught. And here I can say since T observed of 1.87, is that bigger than T critical 2.821? It is not. Since T observed is not bigger than T critical in a right tail test, do not reject H naught. This result might make us suspicious. It might make us feel like maybe the mean sleep time of our students is bigger than 7, but we did not surpass that high bar. We did not provide enough evidence to overcome the null hypothesis. We did not provide statistically significant evidence in favor of the mean being bigger than 7. This could reasonably have happened just by sampling error in a situation where the mean was just 7. So even though 7.64 is a bit above 7, it's not far enough above that we can confidently make the conclusion at the 1% level. So now a question. But I selected green there. OneNote is starting to bug out a little bit. So question. Just out of curiosity, I never want to fail to get a rejection and then go changing alpha, right? I would have set alpha before I did the experiment, done the experiment, get the answer, and that's that. But just out of curiosity, what alpha could I reject at? Could I reject at the 5 or 10% level? Could I make the claim at the 5 or 10% level? Or in other words, what's my p-value? Well, I don't have a normal table, so I can't look up a p-value to like 4 decimal places of accuracy. But I do have a set of indices for the t distribution with 9 degrees of freedom. Right, I compared 1.87 to 2.821, and I can't get my OneNote to move now, but OneNote is just so crashy. But I compared my 1.87 to 2.821 and it failed. It wasn't above 1.8 or 2.821. But I could ask for my t observed of 1.87, what t criticals does it fall between? Well, 1.87 falls on my degrees of freedom 9 line. That's the only one I care about. That's the distribution I'm working under. My 1.87 falls between these two, between 1.833 and 2.262. In other words, 1.87, that t observed is bigger than a t critical of 1.833, but not bigger than a t critical of 2.262. I would be able to reject against the 1.833, but not against the 2.262. In other words, I would be able to reject at the 5% level, but not the 2.5% level. This tells me that my p-value is bigger than or equal to 2.5%, but less than or equal to 5%. I mean, I didn't get it to 4 decimal places, but I could kind of like hack this table and again, figure out, because this is the distribution I'm interested in, and because 1.87, my t observed, falls between these two t criticals. This is a one-tail test. My p-value has to fall between those two numbers. It's got to be between 2.5% and 5%. That's consistent with us not rejecting at the 1% level because p is bigger than alpha. The experienced type 1 error rate would be bigger than the maximum allowable of 1%, but we could reject at the 5 or 10% level had we asked that in the problem statement instead. Okay, that finishes us up for today. Let me stop the recording.